Hi, everyone. Thank you for the amazing introduction, Marcel. That was really neat. I'm going to be talking about statically typing JavaScript. And my talk has 3 to 4 parts. I'm not sure if we're going to have time for the last part. We're going to start with a little bit of a brief recap on type systems, what they are, and some basic ground definitions that I want to talk about. Then we're doing a little bit of a history class. I hope that's interesting for you, on the history of statically typing JavaScript. And then we're going to be talking about the 2 main solutions that are most used in the industry, Flow and TypeScript. And then we're going to be talking about the future of this space. So before I continue, so that I can adjust what I talk about and how in-depth I go about certain topics, can I get a raise of hands from anyone who's using Flow on a day-to-day basis? All right, and TypeScript? Awesome, wow, cool. So what that tells me is that most of you are already applying a lot of the things that we're talking about, and so I'll be a little bit more brief on certain things. So quick recap, I'll try to keep this as succinct as possible. The way I like to think about static typing versus dynamic typing, and there's many ways to put this, but the way I like to think about it is, where does the concept of a type live? If it lives at compile time and it is checked at compile time, you're probably working with a statically typed environment. This is the case of Java, C#, and other traditional statically typed languages. If the concept of a type is checked at runtime, so if the type of a variable or an expression is associated with its runtime values, then you're probably working with a dynamically typed environment. And good examples of this are JavaScript and Python, where the type of a variable or an expression can actually change during runtime. And then you have gradual typing. And gradual typing is sort of new. It's something that came up around 2005, 2006, so it's not really that new. But it basically joins the best of both worlds. And what gradual typing, a lot of people think gradual typing is adding a retrofitted static type system on top of a dynamically typed language, and that's not necessarily true. There are plenty of programming languages that have been gradually typed from the start. And what gradual typing actually is, to me, this is sort of controversial, is the best of both worlds. You have static typing and dynamic typing in the same language, and you basically get this spectrum between dynamic typing and static typing. And if you're working with a gradually typed language, usually you can choose. Do you want to live more over this side, or do you want to live more to the other side? And gradually typed environments let you choose that, sometimes on a per file basis or on a per component basis, which is really nice. And so another definition that I just want to quickly touch on is the definition of a sound type system. This is a more academia term, but we will be using it today during my presentation. And a type system is said to be sound if it rejects all incorrect type states. So in a way, a sound type system is one where there are no runtime type errors, sort of. But it is what the definition is, and we'll be using this definition throughout the talk. And then before we get to the meaty part of the talk, I want to just explain why all of this is relevant. Why do I think it's important to talk about this, and how it sort of relates to you, the JavaScript engineers in this room. So first of all, I really think that static typing helps you with a lot of runtime errors and runtime bugs, because it's very easy for your code to rely on different implicit contracts if they are not checked at compile time. It's too easy to pass the wrong arguments to a function if you don't have static typing. Other things, as Marcel already sort of implied, is that static typing can help you write less tests. Now, you still need tests when you're using a static typing solution, but they can help you write less tests for trivial things such as, does this function reject this argument type? You shouldn't be wasting your time with that type of tests. Then static typing really helps with IDE integration. So you can jump to definition and refactors and all that without static types, but with static types, these usually work better and faster. A good example of this is VS Code, right? So VS Code will use a TypeScript type checker to give you jump to definition and mechanical refactoring on your JavaScript code. But VS Code will give you a lot more than just that if you're actually using TypeScript. And then another cool advantage of static typing, in my opinion, is that your code becomes much more self-documented. So it's much easier for new engineers onboarding onto your code base to understand what's going on. They can just look at an expression, look at a function, see what it receives and what it returns. And then we have the crux of the problem, which is that JavaScript is an extremely dynamic programming language. It has prototypal inheritance, it has implicit type coercion, and it has a lot of other very, very dynamic features. That's why we love it, right? It's because it's so flexible and it allows us to do pretty much anything we want. But that's also what makes it so hard to basically attach a static type system on top of it. It would be too easy to remove all the fun parts of JavaScript and retrofit a static type system on top of that, but it wouldn't be JavaScript anymore. It would be a boring programming language. And so let's try to understand the history, and this is going to be a little bit of a history class. Let's try to understand the history of static typing and why it's so hard to add a static typing solution on top of JavaScript. So the first paper that ever came out on the idea of statically typing JavaScript was actually released in 2005. That was 14 years ago. And in this paper, the author, Peter Thiemann, what he explores is just basically, what he does in his paper is he starts by drawing out a subset of JavaScript that only focuses on object operations. And then what he does is basically try to find type errors. Try to find type errors around object operations. Object property access, object property setting, deleting of object properties. And he basically concludes that it is possible to find type errors. That's pretty obvious. But one of the interesting things that he also says in this paper is that this type of thing, catching type errors in JavaScript, would help JavaScript engineers a lot. So in 2005, Peter Thiemann was sort of predicting the future of what was going to happen here. And one interesting thing about this very first paper is that it was all very theoretical. It was all basically math. There was no prototype, it's just theory. However, 4 years later, Peter Thiemann again and some colleagues wrote the first type analyzer for JavaScript. This was in 2009. They wrote a tool called JS, and it still exists. And what it does is flag suspicious type conversions and certain types of type errors in your JavaScript, based only on type inference. So TJS doesn't require any annotations. It just infers your code, the types of your expressions, and then finds type errors in those in all of your code. But we weren't there yet. And oh, by the way, TJS is still active, it still exists, and it is what academia uses today to basically explore and research anything related to type systems in JavaScript. So a lot of universities and a lot of research groups in various universities build on top of TJS to explore and prototype new ideas of how we can make type systems on top of JavaScript work. And another very important paper by Arjun Guga and two colleagues came out in 2011. And in this paper, what they basically introduce, and I think this is the first time that this was proposed, is what a lot of people nowadays know as type refinements. The idea that the type of a variable or expression can change during the execution of the code. So, put in other words, if you have an if and an else block, the type of an expression could be different inside the if and the else branch. This paper introduced that idea, also known as flow analysis. So analyzing the flow of your code and updating the expected types of variables and expressions along that flow. And one of the most interesting things they say in this paper is that in order to retrofit a type system on top of a dynamically typed language, one must take care so that common idioms aren't deemed untypable. So if we were to add a type system on top of JavaScript, we would have to be very careful not to make common idiomatic JavaScript unacceptable, right? If we want to add a static type system on top of JavaScript, JavaScript code must still be able to be written as usual. And then TypeScript came out, and Flow came out, Flow in 2014 and TypeScript in 2012. And so we basically have this timeline of events. JavaScript was created in 1995. 10 years later, academia started researching the idea of adding a type system on top of JavaScript, or rather a static type system. And then and by the way, there's a lot more research that I didn't include here. There's dozens and dozens, potentially hundreds of papers about this idea. And then the first type analyzer comes out in 2009 by Peter Thiemann's team. And in the same year, Google launched Google Closure Tools. 2009, that was 10 years ago. And in that first release of Google Closure Tools, they already had a type system that could check for type errors. They already had some advanced types like union types and the any type and all other, a lot of other things that we see nowadays in TypeScript and Flow. A couple of years later, Google launches Dart, which is an entirely different approach to this problem. And then TypeScript and Flow came out, and there's still a lot of research going on. I just included this paper here at the bottom. Oh, this is neat. About a lot of the research that's happening nowadays in recent years is how to make TypeScript and Flow even safer, how to make them stricter. That's something that the academia is currently actively researching. So now let's talk about the two main projects that came out of all of this research. Flow and TypeScript are the most widely used tools for statically typing JavaScript. And brief comparison between the two, just very high level, is that TypeScript is backed by Microsoft, whereas Flow is backed by Facebook. They were released between 2012 and 2014. Flow is written in OCaml. TypeScript is written actually TypeScript. They're both actively developed. In fact, Flow just had a release yesterday. TypeScript released an RC yesterday as well. They have different focuses. We'll touch on that in a second. And they're both used by really large projects. So for example, React uses Flow, whereas Angular, VS Code, and Jest use TypeScript. They both support very recent versions of ES 2015 to some extent. And they both can work with Babel, although TypeScript also has its own transpiler. So back to the design goals, which is the fourth row here. Since the very start, Flow and TypeScript have had different design goals. The Flow team at Facebook developed Flow with the intent of type checking the 12 million lines of JavaScript code that they had on their single repository. So obviously, they had to focus on large-scale performance in order to be able to type check all those millions of lines of code in a reasonable amount of time. They also focus on type inference because they knew that in order to start type checking those 12 million lines of code, they needed to have really, really good type inference so that Facebook engineers didn't have to go back and add a lot of type annotations to their code. And to some extent, they also focused a lot on correctness. So one of Flow's design goals since the very start is trying to catch as many errors as possible. So we'll get on that later on. Whereas TypeScript, they also have good type inference, and they also do a lot of correctness checking, but their main focuses have been developer tooling and practicality and adoption. So they have a really good community interaction. They've always been focused on that since day one. It's not just open source, it's open community and open discussion about a lot of topics. So where I work at MemSQL, we've used both Flow and TypeScript in production, and one thing that distinguishes the team that I work on is that we like gradual typing. So we started statically typing our Python in early 2014, and we started statically typing our JavaScript in early 2016. So we have some experience with this. And in particular, we migrated around 40,000 lines of code from Flow to TypeScript around a year ago. And so we've used both on the same project for more than a year each. So we have experience with both of them on the same project. And so let's start to compare. Their syntax is very similar. That's not where their main difference lies. So some basic type definitions look basically the same. Flow has the pipe for sealed objects, but they're actually getting rid of that. So This slide will become basically the same on both sides very soon. And then some of the advanced type definitions are actually slightly different. So the unknown type in TypeScript is called mixed in Flow, and there's a few other differences. In React, you have react.node in Flow, but it's react.react_node in TypeScript. And in TypeScript, you have to name the function arguments on your function types, whereas in Flow, that is optional. So overall, the syntax is very similar. So where are the actual differences between the two of them? They're in the type system and in the different assumptions that both of them make around your code. So as I said at the start, JavaScript is an extremely dynamic language. And when you try to add a static type system on top of that, you have to make compromises. You have to make trade-offs around what you support and what you don't support, what is valid and what is not valid. And so let's try to understand some of these compromises. So let's start with this JavaScript example. In JavaScript, if you multiply null by 3, you get a 0, obviously. And neither Flow nor TypeScript accept this. And you might be wondering, well, why not? It's valid JavaScript. Aren't Flow and TypeScript just JavaScript with a type system? And to some extent they are, but also certain things that you can do in JavaScript are incompatible with what TypeScript and Flow are doing. So both Flow and TypeScript made the right call in not permitting certain types of things that you can do in JavaScript. So this is just an example 0, just to sort of set the stage on what we're going to be talking about next. Let's start with the number 1 example. What should be the return type of this function? It's a pretty simple function, takes in an array of numbers, and it returns the first number in that array. Who can tell me what the return type of this function should be? Yeah, I heard number, and I also heard maybe number and number undefined. That's very interesting. So you are correct. So this function can either return number or undefined. That's it. It can't return anything else. And so the question becomes, should the type checker infer the return type of this function as number or undefined? And according to Flow and TypeScript, the answer is no. It should infer the return type of that function as just number, because making it number or undefined would create too much friction for engineers working with Flow or TypeScript. So both Flow and TypeScript assume that when you index an element from an array, the return type is t, if it is an array of t. So they both went with the option that causes less friction, even though it is technically incorrect. Let's look at another example. We have a type engineer, very simple object type, name and age, and we have a function, we only declare it, so we don't implement it here, called promote engineer that takes in an engineer and returns void. Then we have a type whale with the same properties as a type engineer, and we try to call our promote engineer function, and we pass an object of type whale. Is this code? Do you think this code is valid? In TypeScript it is, yeah, that's right. If you don't think it's valid, you're probably like a Java programmer, because Java would refuse this kind of thing. So as I said, both TypeScript and Flow accept this code. But what about this code? It's technically the same thing, but instead of using object types, we're using classes. And Flow will error. Flow will not accept this, because Flow has what's called nominal typing. So it cares about the names of the types and not the structure of the types, but only for classes. Whereas TypeScript has structural typing for both classes and objects. So we can see already one example of where Flow and TypeScript think differently about your code. They disagree. TypeScript doesn't error on this code. And I don't think either of the approaches is the correct one. I think they're both valid, they're just different. So the Flow design team basically decided that JavaScript engineers, they think nominally about classes, but structurally about objects, whereas the TypeScript design team decided that JavaScript engineers think structurally about everything. Both valid approaches, just different. So now we have another example. We have a function f. It takes in an array of string or number, and it doesn't return anything. And then we declare an array of strings, and we try to call it to the function f. Once again, is this a valid program? I see some people disagreeing and some people agreeing. I'm sorry? It's not a read-only array. That's the crux of the issue here. So TypeScript will not give you any errors on this code, but Flow will error on that line, which I think is very interesting. People in the audience already found out why. It's because you can mutate the array inside the function, and then if you try to access the third element of the array, you get a runtime type error, which is not what was promised by tools like TypeScript and Flow. And as I said, Flow errors on this line, whereas TypeScript doesn't error at all. So what's going on here? TypeScript is being purposefully unsound. This is documented. This is not like a bug or anything. TypeScript is being purposefully unsound because it is more convenient. The truth is that this type of pattern is convenient, and so the TypeScript design team decided to actually not error on that line. You can read more about this on their FAQ. Whereas the Flow team decided that this is not correct. And it is one of their design goals, as I mentioned at the start, that they try to be as sound as possible. So let's look at some type inference examples. I wish I had more. I could have dozens of them, but we just don't have time. So we have a type connection, very simple object type, and then we declare a function called getConnection that returns the connection. And then we implement our own function called resolveConnection, which returns a promise that resolves the output of getConnection. So the return type of this function is promise over connection. But with Flow, I don't have to annotate the return type. I can just call my resolveConnection function, and in the then handler, I can use the con variable as a connection, and I get no errors. But the same code will error in TypeScript, because TypeScript needs a little bit more help with annotations. So it needs you to annotate your function in order for it to understand what's going on here. One more example. We have a type player, soccer player, that has two properties, an age number and a position, which can either be a striker or a goalkeeper. And then we have a function type f, which represents a function that takes no arguments and returns an array of players. With me so far? So then we try to implement a variable of type f. We call it f1, and we declare it as a function that takes no arguments and returns a valid array of players. And Flow will not error. It will understand that the A1 array is a valid array of players, and it will let you do this. It's correct. But the same code will error in TypeScript, because, once again, TypeScript needs a little bit more help with the annotation. TypeScript can't actually automatically detect that this is a valid array of players. So to sum it up, and I know that I showed you very, very small examples, so you're going to have to trust me a little bit on this based on my experience, but in general, Flow has a more powerful type inference than TypeScript. It is better at type inference in general, but with the caveat that TypeScript is catching up. In fact, in certain areas, TypeScript is already better than Flow. And then when it comes to type errors, TypeScript is mostly concerned with striking a balance between program correctness and engineering productivity. In fact, I quoted this from their design goals, whereas Flow is focused on being as sound as possible. And that you can also find that on their design goals. And these differences, they come up all the time when you're working with them. And we migrated 40,000 lines of code from Flow to TypeScript, and so you might be asking why, right? If Flow catches more errors and it has better type inference, why did you switch? I get this question a lot. And the answer is pretty straightforward. One of TypeScript's design goals from the very start was great developer tooling, and this really makes a big difference. So I've become much more productive when working with TypeScript because the developer tooling is just much better. Also, Flow had a much smaller community and no public roadmap, which, as the maintainer of a large project, makes me a little bit scared, right? I'd rather work with tools that I know I can count on for years and years to come. And as an engineer, Flow is an amazing project. It's, technically speaking, it's an insane achievement what they've done. It's really performant. It works really well. But from a more practical point of view, TypeScript is or was the best choice for us, is the best choice for us. But TypeScript is not without its pain points. The performance is noticeably worse than Flow. So for example, whereas with Flow, we would rarely have to wait more than 1 to 2 seconds for a recheck. With TypeScript, we commonly see over 10 seconds for rechecks. It doesn't have partial type argument inference, and in general, the type inference is not as good as Flow's. I'm not going to get into our migration. I have some time. So our migration process, I've documented it, all of it, in a blog post. We had thousands of syntax errors. We fixed all of those. Then we fixed all of our type errors. And we started with a very not strict TypeScript configuration. And since the migration, we have been continuously migrating towards a stricter TypeScript configuration. So every now and then we bump up the strictness of our TypeScript configuration, and it's been working really well for us. So 1 year later, I can definitely say that we made like an amazing decision, despite all the pain involved in the 2 weeks of performing the actual migration. So now I wanted to talk a little bit about the future of statically typing JavaScript. And one of the things that I think I'd like to see discussed as a community is potentially a unified type annotation syntax. So this is one of the things that Python did. They have a unified type annotation syntax, and then in a way, there are multiple type checkers written on top of Python that use the same syntax. And this is nice. It also has drawbacks, but in general, it's an interesting idea, and I'd like to see it explored by the ECMAScript community and the JavaScript community as a whole. And then there's a lot of other things that I would just like to see explored. Some of these are type decorators for annotating deprecated types and other things. Another thing that I would like to see the community discuss is more strictness. So for example, when you start up a new TypeScript project, the strict configuration is set to false. And I believe this was the right call for the first 7 years of the TypeScript project. But now, I think the community is ready for strict set to true by default, or at least I'd like to see that. And so it's something that also I would like to see the community discuss. And then there's other random features that I would just like to see, like variadic kinds to help you with this kind of code, as well as better performance and other things that I would really like to see. And so what are the main takeaways from this talk? The first one is that adding a static type system on top of a dynamic programming language means trade-offs. There is no single way to do it. For Python, for example, there's at least 4 different static type checkers, and they all make different compromises, and they all work differently. For JavaScript, we have around 3 of them, and they also all think differently. So the idea that I want you to take away is that it's a really hard thing to do, and all approaches to this problem will make different compromises. And the different compromises lie around this. So you have to balance usability, which I named as friction, soundness, or correctness, how many errors the type checker is actually catching, and the type check performance itself. And getting all 3 right is basically impossible, and so different type checkers choose different edges on this triangle. Well, this is actually a very basic way to put it. In practice, it's much more nuanced than that. And then after my experience of switching and migrating from Flow to TypeScript, I recommend TypeScript as the most suitable option for most programs. I think there are definitely cases where Flow is better, but in general, I think TypeScript is the best option. And then another big takeaway is that gradual typing is really, really good. I was just having a chat last night about what makes gradual typing so awesome, and the idea of gradual typing is that we as engineers are empowered. We can choose when we want type safety and when we want looseness. So for example, you can write your tests in JavaScript, but you can write your core business logic in Flow or TypeScript. And so you choose when you want strictness and when you don't want strictness. And also, with gradual typing, you get the benefits of type safety whenever you want them, but you can also prototype really quickly, which is really important sometimes. And yeah, I know there's no Q&A, but if you have questions, hit me up on Twitter or email me whenever you want. Thank you very much for your time.